Hello students, in this video we'll see several examples of computing second fundamental forms. The second fundamental form is L du squared plus m du dv plus n v squared. And of course in coordinates, this is going to be r uu dot n hat du squared plus r 2, of course, 2r uv dot n hat du dv plus r vv dot n hat dv squared. That's my form. And so some examples of these second fundamental forms. The first example is a elementary one. So example, if you have r of u and v is a plus bu plus cv, the equation of a plane. And of course, all the second derivatives are 0 because there's only linear terms over here. So that says the second fundamental form of a plane is 0. Actualized. And so of course, first to this too. And so it's that proposition. If the second fundamental form is equal to 0, then the curve is a plane. The surface is a plane. The surface is planar. Okay. How do you do something like that? Prove it there. So relatively straightforward. How would you prove this? Proof. Would move the fact that you can write these things in different ways, that L is really ru dot nu. The negative sign. M is really ru dot n hat v, which is negative, of course, negative of rv dot n hat u. By the computer, part to repeat it. And n is really rv dot nv with a negative factor. On this expression of fear, right? And so what can we say? From these expressions over here, if all these are 0, if L equals M equals N equals 0, then what can I say? Then hence, both N, U hat, and N, V hat are the 0 vector. Since, why is this true? The reason why is that I know that NU and NV are in the tangent plane. This is NU since NU hat and NV hat are in the tangent plane. And for their components are what? Their components, the components of the surface, RU and RV, for example, of NU, are both equal to 0, so they're the 0. Great. All right, now what? So now from this, what can we say? Hence, let's look at r dot n hat. Take the u derivative of this. The ru dot n hat plus r dot nu hat. Of course, ru dot n is equal to 0 because that's a tangent vector, that's a normal vector, that's a 0 by that assumption. And we just proved that nu is equal to 0, so this is 0. But similarly, r dot n hat v equal to what? Is even equal to rv dot n hat plus what? Plus r dot n v. And by the similar, so these are r dot n. So this applies r dot n is a constant vector c with that, or you see not a vector, is a scalar, right? The constant c, and therefore that's the equation of a plane, right? Equation of plane. That's an example. Let's sphere next, right? So how would I find the second fundamental sphere, right? So if we look at the sphere or the unit sphere, you might say, well, that's going to be a long calculation, right? I can parameterize the unit sphere r of u v by cosine of u, sine of v, sine of u, sine of v, and then cosine of v, right? Vector u is going to be, u is going to be r, typically written as r phi. Our v is typically our theta for ordinary sphere coordinates. This. And so you might say, well, how am I going to do this, right? Well, the key feature is that on the sphere, it looks like geometrically, like that. There's the sphere. if I look at the position on the sphere, that's my position on the sphere, that's my r. R is in the same direction as what? R is in the same direction as n hat. R and n hat escape where's bar? R is equal to n hat, right? And so let's use this relationship over here, right? So now what can I say? So I look at RU, for example. So RU implies that RU is going to be n hat u, and RV is going to be n hat v, like this, right? And so what can we say now? We would like to figure out what these things are. So what do we know? We know that, hence, and what? I look at RU is really the same as RU.NU, like this, right? RU.RV is really RU.NB, like this. And then what? And then RV.RV is going to be what? Is going to be RV.NV, like that. Excellent. Of course, these are the components of the first fundamental form, right? These are the components over here of what? Those are the components of my second fundamental form. So for the sphere, the first fundamental form is equal to the second fundamental form. So for the sphere, my first fundamental form, 1, is really what? Is really d theta squared plus what? Plus sine squared of theta d phi squared. And then, of course, the second fundamental form from the unit sphere is the same thing, right? So calculation shows the exact same thing. D theta squared plus sine squared theta d phi squared. So in other words, for the unit sphere, 1 is equal to 2. Their first and second fundamental forms are equal. And when we study principal curvatures, we're going to see that this is actually telling that the principal curvatures of the unit sphere are both equal to 1, right? And we're going to see in further videos how these first fundamental form and second fundamental form relate, and how the ratio of these things is what's going to allow us to define what the Gaussian curvature is. So in particular, the ratio of 2 and 1 is equal to 1. That's going to prove that the Gaussian curvature of the unit sphere is equal to 1, which we'll see in further videos. Thank you very much.